Hello my dear students, this is Akash HD and welcome to the ASD physics classes. So students, I hope so you are regularly watching the series based upon the Coulomb's law and its applications. In this video, we are going to learn electric field properties and its applications and all that. So this is going to be the part 3 of the chapter electric charges and fields. Okay students, so let's start the today's class. Let's learn something. Okay students, so let's start. So the first topic is here electric field. So here this electric field. What is the electric field, students? It is the space around a charge within which it can exert electric force on other charges here. Okay, that means if I draw here the electric field here, remember that one thing, whenever we will learn about the electric field, we will learn in terms of three things. First one, how to draw the electric field lines. Second thing, calculation of the electric field intensity, and third thing, the electric potential. Okay, so first we are going to draw the electric field due to one isolated charge here. Let's take this is the charge plus Q and electric field lines due to this charge plus Q here. Okay, so whenever isolated charge is there, electric field line will be always radially outward here, like this here. Okay, later we will learn in the properties of electric field lines also here. Okay, like this. Is it? Similarly, if in case this is the negative charge, for example here this minus Q charge is there. Now this minus Q charge is there. Now this is the plus Q and here minus Q is there. So in case of minus Q, how to draw the electric field lines here? Like this here. Electric field lines will be like this. Okay, but here what will be there? This electric field lines will be radially inward. Okay, radially inward here. Now due to positive charge, electric field lines radially outward. Due to negative charge, electric field lines are radially inward. If in case we have one conductor, now isolated conductor here. So remember that here inside the conductor, electric field lines will be always 0. And after that, if we draw the electric field lines here, so electric field lines due to the conductors here, this like this. Inside the conductor, electric field lines will not be there. Okay, like this here. Like this, electric field lines will be there due to the conductor. Okay, if in case this conductor is positive charge, then what will happen that here electric field lines will be outward, like this here. Now, so later we are going to learn under the properties of electric field lines also about this conductor. Like what we will learn, electric field inside the conductor will be 0 and electric field lines will be always perpendicular to the conducting surface. Why? Because this conducting surface will act as equipotential surface. Okay, and electric field lines should be always perpendicular to the equipotential surface here. Okay, now after that, as I told you, mathematically electric field intensity and electric potential are the physical quantities that gives us the information about the electric field here. Okay, so students, now first let's learn about the properties of electric field lines here. Okay, properties we are going to see. So properties here, first property, the tangent to a line at any point gives the direction of electric field at that point. Let's take for example here electric field lines like this here. Now, and I want to know the instantaneous direction of the electric field here at point A. That means what I have to do, I have to draw here the tangent here. Similarly, if in case I want to know electric field direction at point B, instantaneous direction, that means here also we have to draw here the electric field, how this tangent here. Okay, second point, students, the relative closeness of EFLs means electric field lines. Okay, so the relative closeness of EFLs indicates the relative strength of the electric field here. Now let's take for example, see the previous diagram here. Now you can see here near to the charge electric field lines are close. That means here electric field is strong. If we go away from the charge, then the closeness between the lines are keep on decreasing. That means strength of the electric field lines also keep on decreasing here. Okay, good. So next one, please students here. EFLs always begins from a positive charge and end on a negative charge. That diagram already I have drawn here. Now let's take like this here. Again I'm drawing here. Plus Q charge means it was like this. Like this it was there, radially outward here. Like this. Radially outward here due to plus Q charge here. But remember that students, one thing, negative charge already I have drawn. But if in case one plus Q and one minus Q charge is there, like a dipole here. Now let's take for example here. This is plus Q and this is minus Q here. Now this is the charge is there. Now which one? Dipole is there actually. Okay, so what will happen that here the field lines will be like this here. No? This is due to the dipole here, like this. No? Here also like this. No? Please remember that here in exam regularly it is coming here. arrow will be towards the negative charge and arrows will be always away from the positive charge here. What is this, students? This is the electric dipole. Now, electric dipole. Later we will learn how to draw the equipotential surface also, but first this electric field lines due to dipole. Okay. After that, students, fourth point, the number of EFLs is proportional to the magnitude of the charge here. That means very simple. If the charge is having the more magnitude, then we have to draw more number of field lines compared to the smaller charge here. Now, let's take for example, we have two charges, 1 coulomb and 2 coulomb. Then what will happen? Due to 2 coulomb charge, number of EFLs will be twice compared to the 1 coulomb charge here. Okay. Please remember that. Very easy actually. Next one is, students, here please. Two EFLs can never intersect each other. Can never intersect each other. Why? Because if in case any two EFLs got intersected, so in this situation what will happen that here at the point of intersection, how many lines are possible? 2 lines are possible, and normally EFL can have only one unique direction here. Now that's why these two directions is not at all possible for the electric field. That's why two EFLs can never intersect each other. Okay, students, next one please. In a uniform field, electric field lines are straight, parallel and uniformly spaced here. Now this thing you have to understand it very well, because number of places we have to draw the uniform electric field lines here. Now, so how to draw here the uniform field? Let's take here. Here I have drawn the 3 lines. And what will happen that here? These 3 lines will be equally spaced here. Now, so this one will indicate which kind of electric field? A uniform electric field. Okay, straight line in one direction here. Okay. 7th one, conservative EFLs can never form closed loop here. What I have telling here, conservative electric field lines here. Now, conservative electric field lines will never form the closed loop here. Later we will see that if in case the electric field is coming due to the change of magnetic field, that kind of electric field is called non-conservative electric field, and it will form the closed loop here. Okay. So students, I hope so all these things are getting very well, you are understanding very well. Now, next one, EFLs always flow from higher to the lower potential. Now, we will learn in the next chapter. 9th one, in a region where is no electric field, EFLs are absent. Like inside the conductor, there is the no electric field. That means here, no need to draw the electric field lines here. Next one, EFLs start and end normally from the surface of conductor, because EFLs are always normal to the equipotential surface. That means, as I told what, a conductor is always having which kind of surface? Equipotential surface here. Now, so if we draw here the electric field lines here, now as we have done before also, so if we draw the electric field lines, what will happen that here? They will be always perpendicular to the surface here. Always how? Perpendicular to the surface. In which direction? If in case this conductor is negative charge here. Which one? Previous one I have taken positive, but now let's take the conductor is negative charge. Then what will happen that here? These arrows will be inward now. Inward arrows. Okay, like this here. So now here we have seen what? Here we have learned the properties of the electric field lines. Next one we are going to learn how to this represent it mathematically here. Now, so let's see here please. Electric field intensity, just like a gravitational field intensity. Now, recently I have uploaded the video, the same concept for this also here. Now, so see here please here. EFI at a point P is defined as electric force exerted on unit charge at that point here. Now, so EFI due to charge capital Q at point P is given by here. That will draw diagram and all that here. But first, according to the first line, electric field at any point is given by force per unit charge here. Now, this is the general formula, equal to F by Q. Now, after that, if in case we have the charge Q here, this charge Q, and here at this point P, I want to calculate the electric field. So what I will do here, first I will draw here the position vector here. Now this is the position vector. Now, and in this direction, let's take unit vector is r cap and the length is r. Now here what I will do here, I will take here one test charge, small q, and you know very well here now both the charges are, this is also positive and this is also positive. That means electric field in which direction? This direction, in the direction of the force here. Now, so this is the direction of the force, and same will be the direction for the electric field also. Please remember that electric field and force always be in which direction? Same direction here. Now, so let's say here please students, if I draw here from here, see, equal to 1 by q, force formula in a vacuum, nothing is mentioned, that means always vacuum or air. That means students, let's see here please, 1 by 4 pi epsilon naught, and from the Coulomb's law, what will write here? Capital Q small q by r square into r cap. Okay, so what will happen? This small q and this small q will cancel out. That means electric field at point P is given by, see please, 1 by 4 pi epsilon naught into q by r square into r cap. Okay, this is the electric field in a vacuum. If in case medium is there, then at the place of epsilon naught, we have to write epsilon, and its value is epsilon naught into epsilon r. Okay, students, good. Next one, let's see here please. Important points of the EFLs here. First one, as we know very well, what is this? EFI is the which kind of quantity? Vector quantity here. Now, and the very important point, second point here please, EFI is always directed towards the negative charge. In case of positive charge, how? Away from the positive charge. Whose EFI to be measured? Very simple. If positive charge, electric field lines are away. Negative charge, electric field lines towards the charge here. Okay, good. Next one please, SI unit. As you know, E equal to F by Q. That means here SI unit is given by here Newton per coulomb, not kg. Newton per coulomb, because E equal to F by Q now. So Newton per coulomb. One more will be there. This also please remember that here volt per meter here. Na? These two SI units are there. Next one please, dimensional formula, students. So this dimensional formula, how to get it here? E equal to F by Q. What I told you? I have told you E equal to F by Q. Correct? So force dimensional formula MLT minus 2. Charge dimensional formula AT. Now, so if we simplify this here, what is the dimensional formula here? See please here. M power 1, L power 1, A will go numerator, A power minus 1 and T power minus 3. Na? Kindly check out here. We are correct? Yes. So this is the dimensional formula of water. This is the dimensional formula of the electric field intensity. Okay. Now, dear students, if in case we have the multiple charges, na? So see here please. EFI at a point due to multiple charges are there. Na? That is called the principle of what? Principle of superposition. Okay. So see here please. EFI at point P due to multiple charges like Q1, Q2, Q3, Q1. How to get it here? Na? So let's see here please, students. Let's take here. I have taken charge Q1, charge Q2. Na? And let's take one charge. I have taken minus Q3. Now this I am going to take the minus so that you can understand more properly here. Minus Q3. Now I am just going to do for the 3 charges. For n charges also we can use, no problem here. Now so let's take for example here. This is point P here. Now so students, let's see here please. Now so from Q1 to P we will draw. Q2 to P we will draw. Why we are drawing all these lines? Because electric field lines or force, they will follow which kind of forces they are, whether electric field is there or electrostatic force is there. Na? They all are following which concept? Central force concept. Na? They are central. So students, if I draw here the directions, so see here please here. Due to positive charge Q1, positive charge means electric field away. Correct. Due to this Q2 also electric field away. Na? And due to this minus Q3 electric field lines, water electric field lines are towards here. Now, so resultant electric field at this point P. Now, resultant electric field at this point P is given by, how to write here? This EP is equal to E1 plus E2 plus E3. If number of charges are there, then plus En. Okay, but everything should be added in a which form? Everything should be added in a vector form here. Okay, good. Next one, let's see here please. What we are going to see, cases of null point due to multiple charges. Now, what do you mean by the null point? Here, null point means wherever electric field is 0 is called water, is called the null point here. Okay, so see here please here. Here I have taken these two diagrams are there. Na? Let's take here for example here, charge Q. Here also charge Q. And here also charge Q here. Now, so what you think electric field intensity at the centroid will be how much here? If I draw like this here, no? Like this, like this. No? So what is happening that they are intersecting here. So at this point, what will happen? Electric field will be 0. Why? Because electric fields will cancel out here. See here please, due to this Q, what will happen? Electric field this side, I have writing E. Due to this Q, electric field this side E. Due to this Q, electric field is this side E. And they all will make how much angle? 120, 120, 120. And what will happen? Resultant electric field at the centroid will be how much? 0 here. At the centroid, center, whatever. Now it will be 0. Similarly here also, if we take the charges Q, Q, Q and Q, then again, what you think students, where the electric field intensity will be 0 here at the centroid. See why? Because here we can see very easily. No? Here we can see very easily. See here, please here. Due to this Q, electric field is away in this direction. Let me change the color, students. No? Due to this Q, electric field in this direction. Due to this Q, electric field in this direction away, and due to this Q, electric field in this direction here. Now, and kindly draw here all equal length here now. So this is cancelled by this one. This is cancelled by this one. That means electric field intensity at the centroid. How much here? 0. Okay, null vector. Null vector. Null vector here. Now here also what we can tell here. Again, I'm telling you this EC how much here? 0 null vector is there. Okay, good. Next one, students, let's see. This one I have covered in a gravitational field concept also, no? And even I have covered in applications of Coulomb's law also. No? So let's see here please. Null point between two like charges Q1 and Q2. Okay. Here charge Q1 and here charge Q2 here. No? And let's take here the distance between the charges. How much I have taken? The distance between the charges I have taken D. So what will happen that here whenever the charges are like, in that situation the null point will always exist between the charges here. No? So let's take here, this is the null point P. No? So at this point what will happen? Electric field intensity will be 0. No? So let's take the null point from the charge Q1 is X. No? And remember that here, this one always used to be the smaller charge here. No? And see this one here. This one, this is the D minus X. So can you tell the direction of the electric field here? No? Let's take here, this is 1 and this is 2. So see here please here at point P, electric field due to Q1 in which direction? Away. What is that here? EP1. Similarly, electric field at point P due to charge Q, how much here? This is EP2 here. So as this is the null point. So null point. So null point, what will happen that here? Null point means both this electric field will cancel out each other. So what we write here? EP1 is equal to EP2. What is the EP1? K, that is the proportionality constant. K into Q1 by X square is equal to K into Q2 by D minus X whole square. So what will happen that here? This K and this K will cancel out. And when you will simplify this X will come here. D by root Q2 by Q1 plus 1. Okay, and remember that this plus 1 is outside of the square root here. Na? Null point between the two which kind of charges? Like charges here. Similarly, in case 3, what we are going to see? Null point between two unlike charges, Q1 and minus Q2. So here what will happen that here? Let's see here. This is charge Q1 and students, this is charge minus Q2. So do you think that electric field can be 0 between the charges? No, it will not be 0. Why? Because see, if I take one example here, let's take here, this I have taken some point A. So see here please, due to charge Q1, electric field away, EA1. Due to charge minus Q2, electric field towards the negative charge. So you can see that here electric field lines are not getting cancelled. That means here the null point is not possible. That means where the null point will be possible? The null point will be possible outside of the charges. You know, let's take for example here, I have taken null point here. So let's take here again, this is point P. The distance of point P from Q1 how much? X. And distance of point P from minus Q2 will be how much here? Guess please, this will be how much here? D plus X. D plus X. Why? Because the distance between the charges, I will take how much? The distance between the charges, I have taken D. Okay. So let's draw the electric field lines due to the different charges. Now let's see here please here. Plus Q1 charge, that means electric field lines away. EP1 minus Q2 charge, that means electric field lines are towards EP2. So again we will write students here, what to write here? As EP1 is equal to EP2. Okay, so again put the value K into Q1 by X square plus, not plus actually, equal to K into Q2. Only we have to write the magnitude, not minus sign at all, only magnitude here, by D plus X whole square. Okay, so what will happen? This K and this K will cancel out, is it? Then what will come here when we will simplify this? This X will come D by square root of Q2 by Q1 minus 1. Okay, and again this distance is from which charge? This distance is from which charge? This distance is from again smaller charge. Which charge? Smaller charge. Now let's take for example, I have the two charges. Now let's take one charge is minus 4 and one charge is 2. Or let's take here, this is the plus 4 and minus 2 I have taken. So tell me please sir, which one is the smaller charge here? Smaller charge, remember that only magnitude here. So this one is the which charge here? This is the smaller charge. smaller charge. Okay, so please remember that here mod q1 should be less than mod q2 here, smaller charge. Okay, good. Next one after that, students, let's see. We are going to see the resultant electric field cases. Up to this we have seen a null point. Now let's see the resultant cases also. So here also, students, in a case 1, here I have taken charge q, and here also I have taken charge q, is it? And at the third vertices, I want to calculate the electric field intensity. Okay, so let's take here, this is 1 and this is 2 here, and all this length are L, L, L. So what you think that here at the third vertices here, at the third vertices here, how many electric field lines are present? Just see please, how many? 2 electric field lines are there. So due to first one you can see, which is in this direction, I will write here E31. And due to charge Q at the vertices 2, it will be this side here. What you write here? This is called E32. So again we have to do here the, which one? Parallelogram method here. Then resultant electric field will be in this direction here. Now let's take here E3 here. And can you guess this angle how much here, students? This angle is 60 degree. Why? Because this angle is also 60 degree here. Okay. So here what will happen that here? This E1 will be how much here? Electric field. Not E1 actually. What is this? E31 actually. E31. So E31 how much here? K into Q by L square. Due to this one here, charge is Q, distance is L. K into Q by L square here. Similarly, what will be the E32, students? E32, it is given by K into Q by R, L square. Both the values are same or different? See please. So both these values are same value. Magnitude is same magnitude. So third one, if I want to calculate the resultant. So resultant is given here. E3 equal to which formula we have to use? 2e cos theta by 2. Number of times we have done here. This theta we will take how much? 60 degree, and it will come here root 3 into e, because 60 by 2, 30 cos 30 root 3 by 2, 2 will cancel out here. So root 3e, that means we can write here root 3 K into Q by L square. This is the resultant electric field in this direction. If you want to write in a vector form, then what you have to do? This magnitude you have to multiply with the j cap. J cap here. Similarly, here also magnitude of the electric field will be same. Only what will be different? Only the directions will be different here. Okay. Next one, students. Case 2. Here what we have done, here we are going to take the 3 charges. In a very basic case, let's take here, this is charge Q, this is charge Q, and this is charge Q here. And here I want to calculate electric field. Especially even in a first part, when I was teaching the Coulomb's law, and later in a second part, Coulomb's law of application, all these things we have covered. You can watch all these things. But there I have taught in terms of which point? Electric force point of view. Okay. So let's give a name here. This is 1, this is 2, and this is 3 here. This is L, this is L, this is L, and this is L. And I want to calculate resultant electric field here at the 4th vertices. So what do you think that here? At the 4th vertices, how many electric field lines will be present? Just here please, how many charges we have? 3 charges. That means we'll be having the 3 electric field lines are there. So see here please here. This one, this electric field how much here? How much here? E41. Due to charge 3, electric field in this direction, what we write here? E43 here. And due to this one, second one, let's just draw the dotted line here. And this will be in this direction here. What we write here? E42. Now we have to calculate the resultant of these 3 electric fields. So we know very well from principle of superposition, resultant electric field at the vertices 4 is given by E41 plus E43 plus E42 here. And this is all vectors. So first what we are going to do, we are going to find out the resultant of 4-1 and 4-3. Then after that we will add up with this one here. So let's take 4-1 and 4-3 is going to give the resultant E4 dash, and this one is going to be added with the E42. So this basics we are going to use here, students. So now what we'll do here, we will find out the magnitude of the individual fields. So which 2 fields are equal? See here please, this E41 and E43. Both are equal. How much it will come here? See please, K into Q by L square, and this one I have taken E. Okay, and one more will write here, this also E42. E42 will be how much here? K into Q by, can you guess this length how much here? This length is the L root 2. Okay, so students, L root 2 whole square. So when you will simplify this, it will come here E by 2 here. Now, so now what we are going to do here, first we are going to find out the resultant. Resultant of which two fields, students? This one here, 4 1 and 4 3. Now, so we'll write here, see, a resultant of E4 1 and E4 3 is. So it is given here E4 dash is equal to, both are equal in magnitude. So 2E cos theta. They are making how much angle? They are making angle 90 degree. So cos theta by 2. Na? So 90 by 2 here. Cos 45 1 by root 2. They will all cancel out. So it will come here root 2E here. Na? And this will be in which direction here? This will be in this direction here. This direction. Now you can see very well this E4 dash and this E4 2 in which direction? They are in same direction. That means they are making how much angle? They are making angle 0 degree here. Na? So again I am writing here resultant of which one? This one. E4 2 and E4 dash is. Na? So overall resultant here E4 equal to E4 dash plus this one here E4 2. Na? Both are in same direction. That's why we are just adding here. So E4 dash how much we have got here? Root 2E. Is it? And E4 2 how much here? E by 2. So just take, simplify this, root 2 plus 1 by 2, E will come. And what is the value of E? The value of E is this one here, KQ by L square here. Na? That means the resultant electric field at the fourth vertices is given by root 2 plus 1 by 2 K into Q by L square. Na? So you can see very well in how much easy manner way we are solving all these basic concepts and all that. Case 3. Sometimes what happened that the charges will be given at the vertices, but they will not be balanced here. Na? Let's take for example here. This is charge Q. This is charge Q, and for example here they have given charge 2Q here. So do you think that now electric field at the centroid is 0? It will not be 0 because this is not the symmetrical charge distribution here. Na? So what we have to do here, we have to make it symmetric. We have to use the concept of symmetric. How to make it symmetric? This is Q, this is Q. If here instead of 2Q, Q is there, then our work can be done. So what will happen that here, this 2Q will write here the Q plus Q here. Na? So this Q and this Q will be adjusted. And what will left now? The only Q will be left. Okay. So we'll draw here the equivalent diagram here. This is the Q, and see here please, this is L, this is L, this is L. That means this length will be how much here? L by root 3 here. Na? So let's take here please, this length how much? L by root 3, and here at the centroid I want to calculate the electric field. So what is the electric field at the centroid? We can get very well here. So EC equal to K into Q by L by root 3 whole square. Okay, like this here. Na? So this is the A, part A. Similarly students, let's take for example here, we have given charges like this. This is given Q, this is given Q, this is given Q, and let's take it is given here minus 3Q. Then what to do? Here also the same concept we have to use here. Na? First let me write here the length L. Na? Let's take here like this here. So now what we have to do here, this minus 3 what we can write here, just guess and tell please here. This one we have to make it Q, then we'll write here Q minus 4Q. Is it? So again this Q, this Q, this Q and this Q, this all will be adjusted. Then what will left here? Only minus 4Q left here. Na? So let me draw here. Here this is minus 4Q, and again this diagonal. Can you guess this diagonal length how much here? This total L root 2. That means this is L root 2 by 2. That means it will come here L by root 2. And again at the centroid, what is the electric field? Same formula. K into charge how much? Only magnitude. 4Q by L by root 2 whole square. Is it? So if in case the charge distribution is not symmetric, electric field at the centroid will not be 0. It will have some value, and there will draw the equivalent diagram here. Next one students, very important concept, simple pendulum in uniform electric field. You know very well simple pendulum we have learned in 11th. What is the time period of the simple pendulum formula? T equal to 2 pi root L by G. And what happens that here? This is the ceiling, and here one pendulum is there that is oscillating. But what happens that sometimes what happens that this bob is having some charge and it is placed in an electric field. Now let me draw here. For example here. Now, here. Let's take for example this is having Q charge here, and this is placed in an electric field in which direction? Electric field in upward direction here. Now, so in this situation what will happen that here, if we draw here, the gravity will act downward direction, but this positive charge will experience one force in which direction? Upward direction here, and because of that one acceleration will come, and acceleration is given by F by m, and it is given by QE by m. Okay, so you can see very well, gravity is downward and acceleration due to the electrostatic force. How much QE by m? In which direction? Opposite direction, is it? So here, this is called the G effective value. What value? G effective value. So G effective value will be how much here? G minus QE by m. Okay, and which formula we will use here? Which formula we will use here? We will use this formula. T equal to 2 pi root L by G effective. And how it will come here? L by, it will come here, G minus QE by m. Similarly, if in case, for example, if in case minus Q charge is there, then what will happen that here? If in case minus Q charge is there, so in case of minus Q charge, I will just write here for minus Q charge, minus Q charge. So in case of minus Q charge, what will be there? Think please. The G in downward direction, but minus Q charge and electric field is upward direction. Then what will happen that here? The force will act in which direction? The force will act in a downward direction here, because negative charge always experiences force in the reverse direction. So because of that force, acceleration is given by here A equal to QE by m, is it? So in this situation, what will happen that here? This G effective value, this one will come here, G plus QE by m here. Okay. And because of that, what is the time period? This time period is going to be 2 pi root L by G plus QE by m. So you have to be very careful whether positive charge is there, negative charge is there, electric field direction is upward or downward. Based upon that, what will happen? The time period of the simple pendulum will change. Okay. So students, now we have reached to the end of this part 3, is it students? So I hope so you have analyzed all these things very well, and based upon this same topic, tomorrow it will be the live class of the part 4. Kindly join and learn a lot of questions of the JEE and NEET exam that has come in a recent years here. Okay, so don't forget to join the live class tomorrow at 6:45 to 7 o'clock. Anyhow, I will start it. Thank you so much. Just kindly comment, share and subscribe to my channel. Thank you so much.